Hi everyone, I'm Valiant Ching. In the last episode, we briefly covered the theoretical knowledge. In this video, let's look at some real-world scenarios related to sockets. These scenarios actually represent some abnormal situations you might encounter while using sockets. Understanding these anomalies is very helpful for us to comprehend, troubleshoot, and address various issues in network operations, while also deepening our understanding of sockets. The first category is what happens when we use a TCP-type socket and the peer process becomes unavailable. In this case, if we had previously established a successful connection and were receiving or writing data, we would receive messages like EOF connection reset by peer or broken pipe, which corresponds to the Linux epipe error code. If we had not yet successfully established a connection, we would receive a connection refused type of error. In actual programming languages, the corresponding error messages look like this. We can see that these errors basically convey the same idea. The connection was rejected. So why would the connection be rejected? This is because, in this scenario, the peer service process has crashed, meaning it no longer exists, but if the machine hosting the process is still running and receives data sent to the unavailable service port, the host will send an RST reset habit to notify the peer that the local service does not exist or has terminated. Continuing to wait is pointless. This is a good practice because the sender can quickly and directly receive the error, perform resource cleanup, and avoid meaningless waiting. It is like when confessing your feelings. In a way, a firm rejection is better than silence. The latter is what truly keeps us on edge. The second scenario is when we use sockets for TCP communication, and the machine hosting the peer service itself crashes, for example, due to flooding, fire, or someone cutting the network cable in between. What happens then? In this case, since the peer service's machine is completely unavailable to us, no response will be sent back. At this point, the sender will follow the default socket configuration, such as the keep alive and timeout related socket options mentioned in the previous video, to wait and retry after sending. If a certain number of retries or time limit is exceeded, an error will be reported and the connection will be terminated. Without setting the socket timeout option, the default number of retransmission attempts is usually 15, with a total duration of around 900 seconds. The interval between each retry follows an exponential back-off algorithm rather than a fixed frequency. If you encounter such time intervals in everyday problems, be sensitive enough. If we don't want to wait that long and prefer to fail quickly with a timeout, we can also adjust the kernel parameter TCP retries to modify this behavior. So what kind of error will we see in this case? There are two scenarios, whether the router substitutes a response or not. If the router does not substitute a response, the local machine will directly report a timeout error. In programming languages, the error looks like this. If the router substitutes a response, it will send back an ICM packet, destination is unreachable, and eventually we will receive an unreachable error, roughly like this. The above describes the case when the machine remains faulty. If the machine recovers midway, the error received will be different. This is because the recovered machine has already lost the original connection information, so it will directly send the reset packet informing us that the peer machine refuses to accept the current or ongoing connection. The corresponding error is similar to the previously mentioned process crash scenario. The third common situation is, what happens if the UDP socket is used and the peer service is unavailable? First, it's important to note that generally, default UDP communication will block indefinitely if the peer service fails, doesn't exist, or drops packets. Therefore, most low-level libraries provide default timeout settings. For example, DNS resolution is 2 seconds. If not, you must pay attention to timeout control in your programming. Also, note that if the UDP packet's destination port is judged as invalid, no service on that port on the target machine, or in other unreachable scenarios, the peer usually replies with an ICMP error message. It doesn't send reset because UDP doesn't have reset packets, similar to the router substituted error mentioned earlier. Since UDP sockets often don't require calling the connect method before sending data, a fundamental difference from TCP, the machine won't have corresponding connection information. Moreover, UDP send to considers the operation successful as long as the data is sent from the buffer. It doesn't care whether the actual return packet contains an error message. Therefore, if an ICMP error message is returned, the original UDP sending process likely won't receive it. This is called the async ICMP error problem. To avoid this, you usually need a daemon process to receive ICMP packet notifications or ensure that connect is called before sending UDP data for further operations. There's also a special scenario worth noting when the data sent through the socket is intercepted by firewall rules, either internally or externally. If there are net filter processing modules on your local network communication path, like IPVS, modules, IPtables, or other firewall modules, you might encounter errors such as EPERM or operation not permitted. When you see these errors, it's likely that the net filter framework in your local protocol stack dropped your packets. If the issue isn't caused by a local firewall but an external one, there are two possibilities. The first is silent packet drops. In this case, it will feel like the remote machine is down, and you'll receive timeout errors. The second possibility is that the firewall sends an reset packet, outright rejecting your connection attempt. This is similar to how a host responds when a process crashes, and you'll get reset or connection refused errors. Alright, in this video, I've covered some common problems and scenarios you're likely to encounter when working with sockets. Understanding these situations will help you better grasp sockets from a practical perspective. It will also give you a clearer approach to troubleshooting when issues arise. If you need more detailed information, you can find a written version of this video in the description. I hope this content has been helpful. Thanks for watching.